Hey everyone, today we're diving into Cloud Identity and Access Management, or IAM, in Google Cloud, specifically for serverless applications. Think of IAM as the gatekeeper of your cloud project, controlling who can access what resources and what actions they can perform. Just like a security guard at a building entrance, IAM checks credentials and permissions before allowing access to your cloud resources. We're focusing specifically on serverless applications, particularly Cloud Run services, where IAM plays a crucial role in securing your containerized applications. Proper IAM configuration is essential for keeping your applications safe and sound. It prevents unauthorized access and ensures that each component has only the permissions it actually needs. Throughout this series, we'll break down the key concepts and best practices you need to know to secure your serverless applications effectively. We'll cover permissions, roles, service accounts, and much more. Cloud IAM has one primary job in your Google Cloud project: managing who can access what. Think of it as the security guard for your entire cloud infrastructure. IAM manages permissions within your Google Cloud project. It acts as the gatekeeper that controls access to all your cloud resources. IAM works through a simple two-step security process. First, it verifies who you are, then it checks what you're allowed to do. Step 1, IAM verifies the identity of whoever is trying to access your resources. This could be a user, a service, or an application. Step 2, once identity is confirmed, IAM checks if that entity has the right permissions to perform the requested action. Here's a practical example. Imagine a service in your application needs to read data from a cloud storage bucket. The service makes a request to read data from the cloud storage bucket. But before this can happen, IAM steps in. IAM acts as a checkpoint. It first verifies that the service is who it claims to be, then checks if it has permission to read from that specific bucket. If both checks pass, identity is verified, and permissions are sufficient, IAM allows the access. The service can now read the data it needs. Here are the key takeaways. IAM is your project's security gatekeeper. It always performs both identity verification and permission checking. Every single resource access in your Google Cloud project goes through IAM. There are no exceptions. Remember, IAM is the foundation of your cloud security. Understanding its primary purpose, managing permissions through identity verification and access control, is essential for building secure serverless applications. The principle of least privilege is a fundamental security best practice in cloud computing. This principle ensures that each service or user gets only the minimum permissions necessary to perform their specific tasks. The core idea is simple. Give each Cloud Run service only the exact permissions it needs to do its job, and nothing more. This minimizes potential security risks. Think of it like this analogy. Imagine you're running a bank and you need to give access to your employees. You wouldn't give a cashier access to the entire bank vault, would you? That would be far more access than they need and creates unnecessary risk. Instead, you give the cashier access only to what they need, the cash register. This is the principle of least privilege in action. Now let's see how this applies to Cloud Run services in Google Cloud. Consider an image processing service. It only needs permission to read images from storage and write the processed results back. It doesn't need database admin rights or billing access. Why is this important? If a service gets compromised, the damage is limited to only what that service can access. If a service with excessive permissions gets compromised, an attacker could access your entire database, modify billing settings, or even delete other services. This creates a massive security breach. But with least privilege, the damage is contained to only what that specific service actually needs. Here are the key takeaways for implementing least privilege in your Cloud Run services. First, start with 0 permissions and add only what's absolutely necessary. Second, regularly review and remove any unused permissions. Third, use specific roles rather than broad admin access. And finally, always test your services with minimal permissions first to ensure they work correctly. Remember, the principle of least privilege is your first line of defense against security breaches. By limiting access to only what each service truly needs, you create a more secure and manageable cloud environment. Understanding the difference between permissions and roles is fundamental to Cloud IAM. Think of it like the difference between individual tasks and job descriptions. Permissions are specific actions you can perform on a resource. Each permission represents one particular thing you're allowed to do. For example, with a cloud storage bucket, you might have separate permissions to read files, write files, delete files, or list the contents. Each is a distinct action. Now, imagine if you had to assign each of these permissions individually to every user. That would be very tedious and error-prone for managing access. This is where roles come in. A role is a collection of related permissions grouped together. Instead of assigning permissions one by one, you assign entire roles. Think of a role like a job title. A storage admin role might include all the permissions needed to fully manage storage resources. Similarly, you might have a storage viewer role that only includes read and list permissions, perfect for users who just need to view files. The job title analogy makes this clear. The role is like the job title, and the permissions are the specific tasks that job can perform. In Cloud IAM, roles work the same way. The role is the title you assign, and it automatically includes all the permissions that role needs to do its job. This makes access management much easier. Instead of tracking hundreds of individual permissions, you work with meaningful role names that clearly describe what someone can do. Policy bindings are the fundamental building blocks that connect identities to permissions in Cloud IAM. Think of them as the bridge that grants access to your cloud resources. Every policy binding has three essential components. First, a member. This is the identity that needs access, like a user or service account. Second, a role. This defines what permissions are granted, like the ability to invoke a service or read from storage. Third, a resource. This is what the member gains access to, such as a specific Cloud Run service or an entire project. Now let's see this in action with a practical example that you'll commonly encounter when working with Cloud Run services. Here's a common scenario. You have a service account that needs to call a Cloud Run service. The service account is our member. The Cloud Run invoker role contains the specific permissions needed to call Cloud Run services. This is our role component. The Cloud Run service itself is our resource, the thing we want to access. The policy binding connects all three together. The policy binding creates this relationship, effectively saying, this service account has Cloud Run invoker permissions on this specific service. Let's wrap up with the key points you need to remember about policy bindings. First, policy bindings are the essential glue that connects identities to permissions in Cloud IAM. Without them, no access is granted. Second, every policy binding always contains these three components: a member, a role, and a resource. All three are required. Third, each policy binding represents one specific access grant. If you need multiple permissions, you'll need multiple bindings. Finally, understanding policy bindings is essential for properly securing your serverless applications and following the principle of least privilege. Understanding the difference between service accounts and Google accounts is crucial for cloud security. These two types of identities serve very different purposes in Google Cloud. A Google account is what you, as a human user, use to log into Google Cloud. It's tied to your personal or work email address and represents your individual identity. A service account, on the other hand, is a non-personal identity designed specifically for cloud resources like applications and virtual machines. It's not tied to any human user. Let me show you how service accounts work in practice with some concrete examples from Google Cloud Services. When you deploy a Cloud Run service, it automatically gets assigned a service account. This service account allows your application to make API calls to other Google Cloud services without any manual authentication. Similarly, when you create a Compute Engine virtual machine, it also gets a service account. This allows the VM to authenticate with Google Cloud Services automatically without storing any credentials in your code. The key advantage of service accounts is automation. Your cloud resources can authenticate and make API calls without any human intervention, making your applications more secure and easier to manage. The default service account in Google Cloud comes with the project editor role, which creates a significant security vulnerability. Understanding why this is dangerous is crucial for securing your serverless applications. Every Google Cloud project automatically creates a default service account. This account is typically assigned the project editor role, which grants extensive permissions across your entire project. The project editor role grants read and write access to almost all resources in your project. This includes Cloud Run services, cloud storage buckets, databases, compute instances, IAM settings, and even billing information. If an attacker compromises a service using the default service account, they gain project editor permissions. This means they could delete critical data, modify database settings, spin up expensive compute resources, change security permissions, or access sensitive billing information. Instead of using the default service account, create custom service accounts with specific roles. Give each service only the minimum permissions it needs to function. This way, if one service is compromised, the damage is contained to only what that service actually needs to access. Remember these key points. The default service account comes with dangerous project editor permissions. If compromised, attackers gain broad access to your project. Always create custom service accounts with only the specific permissions each service needs. This follows the principle of least privilege and significantly improves your security posture. When you first deploy a Cloud Run service, it's private by default. This means only authorized users and services can access it. But what if you want to make your service publicly accessible to anyone on the internet? To make a Cloud Run service public, you need to create a policy binding. A policy binding has three key components that work together. First, we have the special group called All Users. This represents everyone on the internet, literally anyone who can reach your service URL. Second, we have the Cloud Run Invoker role. This role grants the specific permission needed to call or invoke your Cloud Run service. The policy binding connects these two components together. It says, give the All Users group the Cloud Run Invoker role for this specific service. Here's what happens when you apply this policy binding. Before the binding, your service is private and locked down. After applying the policy binding that connects all users to the Cloud Run Invoker role, your service becomes publicly accessible. Anyone with the service URL can now call it. Be very careful when making a service publicly accessible. Once you apply this policy binding, your service is open to the entire internet. Anyone who knows your service URL can call it, which can lead to unexpected costs, security vulnerabilities, or abuse. Remember, the combination of the All Users group and the Cloud Run Invoker role creates public access. Use this power responsibly and only for services that are truly meant to be public-facing. When working with private Cloud Run services, you need a way to prove your identity. This is where ID tokens come into play as your digital proof of authentication. An ID token is a secure, digitally signed piece of data that proves who you are. Think of it like a digital passport that contains your identity information in a format that Cloud Run can verify and trust. Here's how ID tokens work with private Cloud Run services. When you make a request, you include the ID token in the HTTP header as a bearer token. This tells the service exactly who is making the request. The authentication flow works in 3 simple steps. First, your client includes the ID token in the request header. Then, Cloud Run receives the request and extracts the token. Finally, Cloud IAM verifies the token to ensure you're authorized to access the service. Here are the key takeaways about ID tokens. They provide secure authentication for private services, must be included as bearer tokens in HTTP headers, are verified by Cloud IAM for authorization, and have expiration times for security. Understanding ID tokens is essential for building secure serverless applications. The Google Front-End Server, or GFE, is a critical component that most developers never see but plays a vital role in securing your Cloud Run applications. Think of the GFE as the front door to Google Cloud. Every single HTTPS request that comes to your Cloud Run service must first pass through this security checkpoint. Here's how it works. When a client sends an HTTPS request to your Cloud Run service, it doesn't go directly there. Instead, it first hits the GFE server, which processes and secures the request before forwarding it. The GFE performs 4 critical security functions that protect your application before any request reaches your code. First, it handles TLS encryption. The GFE manages all SSL certificates and ensures that communication between clients and Google Cloud is encrypted and secure. Second, it provides DDoS protection. The GFE can detect and filter out malicious traffic patterns, protecting your application from distributed denial of service attacks. Third, it inspects authorization headers. The GFE examines authentication tokens and validates that requests have proper credentials before they reach your service. Finally, it removes internal HTTP headers. The GFE strips away any internal Google infrastructure headers that shouldn't be exposed to your application, maintaining security boundaries. The key takeaway is that the GFE acts as your invisible security guardian. It's automatically protecting every Cloud Run service you deploy, handling security concerns before requests ever reach your application code. This is part of what makes Google Cloud's security model so robust. Docker Compose is a powerful tool that makes local development of multi-container applications much simpler. Think of it as a conductor orchestrating multiple Docker containers to work together seamlessly. Docker Compose allows you to define and run multi-container applications. Instead of manually starting each container separately, you can orchestrate them together, create virtual networks between services, and dramatically simplify your local development workflow. Here's how Docker Compose orchestrates multiple containers. You might have a front-end service, a back-end API, and a database service. Docker Compose creates a virtual network that allows these containers to communicate with each other seamlessly. Docker Compose uses a simple YAML file to define your application stack. You specify each service, how to build or run it, which ports to expose, and Docker Compose handles the rest. This single file replaces complex manual container management. For Cloud Run development, Docker Compose provides incredible benefits. You can test multi-service interactions locally, mirror your production environment structure, enjoy faster development cycles, make debugging easier, and ensure consistent development across your entire team. Remember these key points. Docker Compose orchestrates multiple containers seamlessly, creates virtual networks that enable service communication, and dramatically simplifies local development of Cloud Run applications. It's an essential tool for modern serverless development workflows. Let's explore why the principle of least privilege is so critical through a real-world example. Imagine you have a Cloud Run service that only needs to read data from one specific cloud storage bucket. The correct approach is to give this service only the minimum permissions it needs. Read access to just that one specific bucket. This follows the principle of least privilege. Now let's see what happens with the wrong approach. If you give this service the project editor role, it gets far more permissions than it needs, including the ability to delete all buckets in your project. Here's where the danger becomes clear. If this overprivileged service gets compromised by an attacker, they don't just get access to the one bucket the service actually needs. The compromised service can now delete all your buckets, not just the one it was supposed to read from. This could destroy your entire data storage, causing catastrophic damage to your business. This catastrophic scenario could have been completely prevented by following the principle of least privilege from the beginning. The key takeaway is simple but critical. Always give your services only the minimum permissions they need to function. This limits the potential damage if something goes wrong. In Cloud IAM, you can bind roles to 4 different types of members. Each member type serves a specific purpose and has its own best practices for when to use it. Here are the 4 member types you can choose from. Each serves a different purpose in your IAM strategy. First, Google accounts are for individual users. When Sarah from your development team needs access to cloud storage, you bind the Storage Object Viewer role directly to her Google account email address. Groups are perfect for managing team permissions. Instead of assigning roles to each developer individually, create a developers group and assign the role once. When new team members join or leave, just update the group membership. Service accounts are for your cloud resources and applications. When your Cloud Run service needs to access Cloud SQL, you create a service account with the Cloud SQL client role and assign it to your service. This follows the principle of least privilege. Finally, all users should be used very carefully and only when you explicitly want to make something public. For example, a public API or website that anyone on the internet should be able to access. Use this sparingly and always review these permissions regularly. To summarize, use Google accounts for individual users, groups for teams, service accounts for cloud resources, and all users only for truly public services. Choose the right member type based on who or what needs access, and always follow the principle of least privilege. When you have multiple Cloud Run services that need to communicate with each other, you need a secure way to ensure only authorized services can make requests. This is where IAM and ID tokens come into play. Let's say we have service A that needs to call service B. Without proper security, any service could potentially access service B, which creates a security risk. The problem is that without authentication, service B has no way to verify that the request is actually coming from an authorized source. Step 1. Give service A a dedicated service account. This service account will act as the identity for service A when making requests to other services. This service account becomes the authenticated identity that service A will use for all its outbound requests. Step 2. Grant the service account the Cloud Run Invoker role specifically for service B. This role gives permission to invoke or call the target service. This follows the principle of least privilege. Service A only gets the minimum permissions needed to call service B, nothing more. Step 3. When service A needs to call service B, it first obtains an ID token using its service account credentials. The ID token is a JSON web token that contains information about the service account and proves its identity. Service A then includes this ID token in the authorization header of its HTTP request to service B. Step 4. Service B receives the request and verifies the ID token. It checks that the token is valid, hasn't expired, and comes from an authorized service account. If the token is valid and the service account has the correct permissions, service B grants access and processes the request. Here are the key takeaways. Service accounts provide identity for your services. The Cloud Run Invoker role grants the specific permission to call other services. ID tokens prove authentication in requests, and target services must verify these tokens before granting access. This approach ensures that only authorized services can communicate with each other, creating a secure service-to-service authentication system in your Cloud Run environment. The Google Frontend Server, or GFE, plays an important role in Google Cloud's infrastructure, but it's crucial to understand that it's not a traditional security perimeter that protects everything for you. The GFE server does provide several important security functions. It handles TLS encryption for secure connections, provides DDoS protection against attacks, and performs basic authorization checks. However, these protections are just the first layer. The GFE is not a comprehensive security solution that handles all your application's security needs. Your application must still implement robust security measures. This includes input validation to prevent malicious data from entering your system. You need proper authentication mechanisms to verify user identities beyond what the GFE provides. Data validation ensures that the information your application processes meets your business requirements and security standards. And you must secure your business logic to prevent unauthorized access to sensitive operations and data. Let me give you a practical example to illustrate this concept. Imagine a user sending a request to your Cloud Run service. The request first goes through the GFE server. The GFE handles TLS termination and basic checks, then forwards the request to your application. The GFE handles the network-level security, but your application must still validate inputs, authenticate users, check permissions, and sanitize data. Here are the key takeaways you should remember about the GFE server. First, the GFE provides important but limited security functions. It's your first line of defense, not your only one. Second, it's not a comprehensive security perimeter that handles all threats. Third, your application must implement its own security measures for complete protection. And finally, never rely solely on infrastructure-level protections. Defense in depth is essential for robust security. Inter-service communication is a critical aspect of serverless applications that can make or break your application's performance. Today, we'll explore the lessons learned from real-world latency challenges. In synchronous communication, Service A must wait for Service B to complete its work before continuing. This creates a chain of dependencies that can lead to significant performance bottlenecks. The problem becomes worse when you have multiple services in the chain. Each service adds its own latency, and if any service in the chain fails or becomes slow, it affects the entire request flow. Now let's clear this and look at a better approach. Asynchronous communication allows services to continue processing without waiting for immediate responses, significantly improving overall performance. In asynchronous communication, Service A sends a message to a queue and immediately continues processing. Service B processes the message when it's ready, eliminating the blocking behavior. Another important lesson is the difference between fine-grained and coarse-grained integration. Let's compare these two approaches and their impact on performance. Fine-grained integration involves many small, frequent calls between services. While this provides flexibility, it can create significant network overhead and latency issues. Coarse-grained integration uses fewer, larger interactions between services. This reduces network overhead and can significantly improve performance, though it requires more careful design. However, there's an important trade-off to consider. While asynchronous and coarse-grained approaches improve performance, they can make data consistency more challenging to maintain across services. Let's summarize the key takeaways from these inter-service latency lessons. These insights will help you design more efficient serverless applications. Understanding these inter-service communication patterns is crucial for building high-performance serverless applications. The right choice depends on your specific requirements for latency, consistency, and scalability. Cloud IAM serves as the security foundation for your entire Google Cloud project. Just like a building needs a strong foundation to support everything above it, your cloud applications need IAM to provide secure access control. What makes Cloud IAM so foundational? It provides three core components that work together to secure your project. First, permissions define what actions can be performed on resources. Second, roles group related permissions together. Third, policy bindings determine who gets which roles. For serverless applications with CloudRun, IAM provides multiple layers of protection. Let me show you how this works in practice. Your CloudRun service uses a service account with only the minimum permissions needed. IAM ensures it can access the database and storage it needs, but nothing more. Following the principle of least privilege is crucial. This means granting only the minimum permissions necessary for each component to function. Here are the key best practices for using Cloud IAM as your security foundation. Always use least privilege, create custom service accounts, avoid defaults, audit regularly, and prefer predefined roles. Remember, Cloud IAM is not just another security feature. It's the foundation that everything else builds upon. When implemented correctly with least privilege principles, it enables you to build secure, reliable serverless applications with confidence. Cloud Identity and Access Management, or IAM, is a fundamental service in Google Cloud that controls who can access what resources in your project. Think of IAM as the security system for your Google Cloud project. It determines who gets access to which resources and what they can do with them. Let me explain this with a simple analogy. Imagine your Google Cloud project is like a secure office building. IAM acts like a security guard who checks everyone's credentials before letting them into different parts of the building. The security guard checks who you are, what permissions you have, and then decides whether to grant you access to specific resources. Here are the key things to remember about Cloud IAM. First, IAM controls who can access your Google Cloud resources. This includes users, service accounts, and groups. Second, it manages what actions they can perform once they have access. This could be reading data, creating resources, or deleting files. Third, IAM works at the project level and can extend to organization and folder levels for enterprise setups. Finally, IAM is essential for security and compliance, helping you follow the principle of least privilege and meet regulatory requirements. Remember, Cloud IAM is your first line of defense in securing your Google Cloud environment. It's the foundation that everything else builds upon. The principle of least privilege is a fundamental security concept that every developer should understand. It's simple but powerful. Give each user or service only the minimum permissions they actually need. Think of it like office keys. A janitor needs access to cleaning supplies, but doesn't need keys to the company's safe or CEO's office. Giving unnecessary access creates security risks. In Cloud IAM, this means each service gets only the permissions it needs. A web service might read from a database and write logs, but it doesn't need admin access to create new projects. Following least privilege reduces your attack surface, limits damage if something goes wrong, and makes your system easier to audit and manage. Remember, start with 0 permissions and add only what's absolutely necessary. This approach keeps your Cloud IAM secure and manageable. In Cloud IAM, a permission represents a very specific, granular operation that can be performed on a particular resource. Think of permissions as the individual building blocks of access control. What makes permissions special is that they're usually tied directly to specific API endpoints. When you make an API call to Google Cloud, that call requires a specific permission to succeed. Here are some concrete examples of permissions. Notice how specific each one is. Storage.objects.list allows you to list objects in a storage bucket. Compute.instances.create lets you create virtual machines. Each permission controls exactly one type of operation. The granular nature of permissions is crucial for security. Instead of giving broad access like full storage access, you can grant only the specific permission needed, like storage.objects.list. This granular approach follows the principle of least privilege, giving users only the minimum access they need. Remember these key points about permissions. They represent specific operations you can perform. Each permission is typically tied to an API endpoint, and they serve as the fundamental building blocks of Cloud IAM access control. Understanding permissions helps you implement proper security in your serverless applications. In Cloud IAM, a role is a collection of permissions that makes it easier to manage and reason about access control. Instead of assigning individual permissions one by one, roles group related permissions together for simpler management. Imagine you have individual permissions scattered around. Each permission grants access to a specific action, like reading storage objects, creating new objects, deleting objects, or listing storage buckets. These individual permissions can be grouped together into a role. For example, all these storage-related permissions might be combined into a storage admin role. This makes it much easier to understand what access someone has. Cloud IAM provides many predefined roles. For example, the viewer role gives read-only access, the editor role provides read and write access, and the owner role grants full control. Each role contains dozens of specific permissions grouped logically. Roles provide several key benefits. They're easier to manage because you assign one role instead of many individual permissions. Role names clearly describe their purpose, making access control more understandable. And roles ensure consistent access patterns across your entire project. The key takeaway is that roles are collections of permissions that make Cloud IAM simpler and more manageable. Instead of dealing with hundreds of individual permissions, you work with meaningful roles that clearly communicate their intended purpose. Policy binding is a fundamental concept in Cloud IAM. It's the mechanism that connects a member to a role on a specific resource, granting that member the permissions defined by the role. A policy binding has 3 essential components. First, we have a member. This could be a user, service account, or group that needs access to something. Second, we have a role. This defines what permissions are granted, like viewer, editor, or a custom role with specific capabilities. Third, we have a resource. This is what the member is getting access to, such as a Cloud Run service, storage bucket, or entire project. The policy binding is what connects these 3 components together. It creates the relationship that says this specific member has this specific role on this specific resource. Here's a concrete example. We create a policy binding where Alice at company.com is the member, Cloud Run Invoker is the role, and my -API-service is the resource. The result of this policy binding is that Alice can invoke the MyAPI service, but she cannot modify or delete it. The binding grants exactly the permissions defined by the Cloud Run Invoker role, nothing more. Here are the key takeaways about policy bindings. They are the glue of Cloud IAM, connecting who gets what access to where. Each binding is specific to one resource, but you can have multiple bindings for the same member across different resources or with different roles. That wraps up our comprehensive study guide on Cloud IAM for serverless applications. As we conclude this journey together, let's review the essential concepts that will help you build secure and scalable applications in Google Cloud. First and most importantly, always apply the principle of least privilege. This fundamental security concept means granting only the minimum permissions necessary for each task or service to function properly. Second, make sure you understand the crucial difference between permissions and roles. Remember that permissions are specific actions you can perform, while roles are collections of related permissions bundled together for convenience. Third, use service accounts wisely. Avoid the temptation to use default service accounts with broad permissions. Instead, create specific service accounts for each service with only the permissions they actually need. As you continue building serverless applications, remember these essential security best practices. Use policy bindings effectively to connect the right members with appropriate roles. Regularly audit your IAM policies to ensure they still meet your security requirements. Always implement proper authentication mechanisms for private services using ID tokens. And don't forget to test your security configurations thoroughly before deploying to production. By mastering these Cloud IAM concepts, you now have a solid foundation to build secure and scalable serverless applications in Google Cloud. You understand how to properly manage access, implement security best practices, and protect your applications from common vulnerabilities. Remember, security is not a one-time setup, but an ongoing practice. Keep learning about new security features, stay updated with best practices, and continue building amazing applications. Keep learning, keep building, and most importantly, keep securing. Thank you for joining me on this Cloud IAM journey. I hope this study guide has been helpful in your serverless development adventure. Good luck with your future projects.